In this video, I'm going to give some math explanation about Chen fountain. First, this is the model of the Chen fountain at steady state. Means it won't significantly rise up when it arrives this height. Then I simulate the Chen outside the part 2 above part with gray color and below part with red color. Above part started from the center of this ball. There is another part inside the pot with green color. I call it rigid in our previous video. This rigid is made out of two balls whose diameter is d and one rod connected length. The link length is L minus d, so the whole length from here to here is L. We assume three kinds of force. Weight is W above and W below, respectively, for gray part and red part. And the force F is the force between link. And F is all same. These F are all at same value but different direction. And also the reaction force F1, which is the main reason for the Chen fountain. Another claim is the speed of the whole chain is same, otherwise the chain cannot move fluently. So our goal is from initial condition L and D to calculate how high the chain can fly. Now we can set three equations for these three parts. For the red part, since the all balls move with same velocity, so it is at static equilibrium. For the gray part, it is subject to three forces: F downward from its two ends and W above at the center. And from Newton's second law, we can derive the relation between mass density and force. So here is the second equation. 2 times W below plus W above is equal to 2 lambda velocity squared. And also for green part, we get another equation is F1 plus F is equal to lambda V squared. And if we ignore the curve here, we can combine these three equations and get the h above over h below is equal to F1 over F. Now we zoom in to analyze F1 and F from Newton's second law. We can set these two equations about velocity and angular velocity about the center of mass. And we still have to find the relation between velocity and angular velocity to solve these two equations. For velocity of the left side board, since it will keep contacting flow, its vertical velocity is 0, and is also equal to V minus R omega. From the equation above, we get the relation between F and F1. The first term is nothing to do with theta, so it's called initial reaction force. And as theta gets larger, the reaction force will decrease until it arrives at a critical angle, so that F1 is equal to 0. It means that the left ball is starting to leave floor and pull the next ball. But the result looks a little bit complex and includes angular velocity, which is hard to calculate, so we have to simplify the equation. To approximate F1, we ignore the second and third part of the equation, and we assume that theta is at small angle, so that cosine theta is nearly equal to 1, and sine theta is equal to theta. Finally, we can get the relation between the ratio of height and initial condition. Note that this ratio is fixed if initial condition doesn't change. So when we put the part higher, the train will fly higher.